A statement from Carlos's instructor in Durham School. I've committed my whole calling to empowering an explicit hypothesis about the universe. Then, at that point this happens, the hypothesis is being kept an eye on. I embrace this test because it is through such looking that we progress and improve in science. The James Webb Space Telescope is essentially upsetting some long-held cosmological convictions that have been perceived as truth for 100 years. One more ultra-deep image has revealed that we have committed errors in space science. The telescope, which was planned to expose the main stars of the universe, is genuinely problematic. The past perspective could present a totally new historical viewpoint. Not all specialists are lamenting these new divulgences. Different experts are inviting these degrees of progress since it has, for a significant length of time, been clear that there were issues with our past theories. The anomalies in surveying the universe's pace of enhancement alone should have brought caution up for any specialists a shockingly long time ago. As opposed to precisely unwinding these alerts, many stuck to obsolete theories. The cosmic microwave background radiation, CMB, which is the most ancient light in the universe, was made about 380,000 years after the Big Bang, when the universe had sufficiently cooled for electrons and protons to form stable hydrogen particles. This change, known as reionization, made the universe easy to illuminate. The CMB was first identified in 1964 by American physicists Arno Penzias and Robert Wilson as they dealt with new innovations in radio collecting. They experienced a steady clamor coming from every direction. At first, this revelation was regarded as solid evidence for the theory of the universe's origin. Penzias and Wilson were awarded the Nobel Prize, and their discoveries turned into a significant establishment in space science. The CMB's history in space science probably gives a brief look into the early universe, with minute temperature changes offering fundamental pieces of information regarding the circumstances after the Big Bang. Researchers utilized the CMB as a reliable marker to gauge huge bits of the material universe, including the rate of its expansion. In the past, Edwin Hubble had made such evaluations in the late 1920s. He saw that far-off cosmic systems were moving away from us everywhere and that their speed was connected with their distance, a relationship now known as the Hubble constant or Hubble's law. Notwithstanding the fact that Hubble's evaluations were not as exact as they are today, they were significant. When the CMB was found, specialists recalculated the expansion rate, viewing it as fundamentally lower than Hubble's initial appraisal. Subsequent recalculations, utilizing type Ia supernovae as standard candles, gave a more exact gauge. Anyway, errors remained, and the contrast in expansion rate estimates has existed since the 1990s. Specialists have guessed that there may be issues with the CMB data analysis techniques or the idea of general expansion. This uniqueness, known as the S8 tension or Hubble tension, suggests that our understanding of the universe may be fundamentally flawed. Since the James Webb Space Telescope, JWST, began its operations, it has provided exceptional data that could help make sense of the issue. Galaxies so old and mature that their formation may hypothetically have started before the Big Bang are challenging long-held scientific theories. Astronomy now faces what is considered to be the greatest crisis in modern cosmology. The rate of expansion of the universe and the hypothesis of how things came to be are under extreme investigation. New images reveal a universe that differs fundamentally from past models. The S8 tension has served as an early warning for specialists who still cling to old theories, now struggling with the realization that our understanding of the universe may be incomplete. This uncertainty has left many researchers troubled and frustrated. To address this crisis, we must understand how science functions. Theoretical scientists use a combination of mathematical models, observational data, and logical reasoning to arrive at conclusions. Their insight comes from observing anomalies, test results, and theoretical analysis. The term theory itself suggests developments and ideas rather than absolute truths. Our rational knowledge comes from images provided by telescopes, sound waves, and radiation captured by radio telescopes, as well as data from neutrinos and gravitational waves. The James Webb Space Telescope allows us to break down the oldest light into individual frequencies and analyze it in incredible detail. It can determine which elements were present in galaxies billions of years ago, the mass contained within them, and the number of stars present. However, Webb's images may have limitations, such as the inability to effectively distinguish between galaxies and black holes that produce similar brightness anomalies due to gravitational lensing. Our understanding has advanced to consider different possible outcomes, as scientists frequently dismiss alternative explanations. New revelations from the James Webb Telescope offer crucial insights that could lead to replacing old theories with new knowledge. Scientists are currently grappling with these discoveries, which seem so extraordinary that finding new explanations is proving challenging. The most recent findings are shaking the foundations of physics, causing concern among many specialists. Physics standards today are still strongly influenced by Isaac Newton's 17th-century work. For a long time, his laws of motion and gravity provided the foundation for understanding the physical world. Newton's rules of the universe function well under normal conditions on Earth. However, in space, his ideas required expansion, largely achieved by Albert Einstein during the 20th century. Einstein's special theory of relativity, published in 1905, revolutionized our understanding of space and time. How might we approach reality television? The laws of physical science are, in comparison to the movement of the observer, central to Einstein's general theory of relativity. Published in 1915, this theory expanded concepts with numerical forecasts of anomalies in the gravitational field, considering the curvature of spacetime caused by massive objects like stars or galaxies. While Einstein's speculations were clear in many areas, he recognized their limits and sought a unifying structure. However, no researcher has yet succeeded in this endeavor. It is interesting to consider where the errors might lie. Michio Kaku, a notable American astrophysicist, suggested that solving this issue could earn a Nobel Prize. We need to investigate whether reality has been misconstrued, whether there have been misinterpretations of anomalies, or if telescopes themselves may be to blame. Dark matter and dark energy are prime suspects in the cosmological mystery. Current models propose that dark matter and dark energy together account for around 95% of the universe. However, neither has been directly observed or definitively proven to exist. They may not exist at all or may possess properties we do not yet understand. One possibility under examination is that dark matter's properties could have evolved over time, potentially exhibiting some form of intelligence. While gravity should cause attraction through mass, spacetime has not been definitively shown to behave as expected in all cases. Despite the fact that Einstein's spacetime bending theories have been validated multiple times, we cannot completely rule out the possibility that gravity has unexpected properties or that another force is responsible for gravitational attraction. Over time, certain constants in cosmology and space science have been regarded as fundamental and dependable due to their consistency. However, slight variations in these constants could provide new insights into the universe, potentially explaining anomalies without the need for dark energy. It is also possible that our interpretations of light shifts have been incorrect, leading to errors in distance measurements and galaxy age estimations. Perhaps our assumptions about the universe's origins are flawed, or we have misinterpreted the cosmic microwave background radiation. Additionally, the universe may not have originated from a single point, challenging the Big Bang theory. Small errors in the James Webb Space Telescope or other observational instruments cannot be ruled out. Scientists acknowledge that mistakes in instrumentation, data processing, or interpretation are always possible. The continual re-evaluation of cosmological theories underscores the fundamental nature of scientific progress, the ability to adapt and refine our understanding in response to new evidence. The James Webb Space Telescope's observations are more than just a technological leap. They mark a significant moment in our quest to unravel the universe's secrets. As we grapple with these discoveries, it is crucial to consider their broader implications. The process of refining cosmological theories is often driven by the need to align speculation with new insights. The emergence of peculiar anomalies in established models can be unsettling, but it also presents opportunities for scientific advancement. Theoretical models in cosmology provide a structured understanding of the universe's origins, development, and evolution. However, as new data emerges, these models must be tested and, if necessary, revised to accommodate new insights. One significant area of focus is the nature of dark matter and dark energy, which are fundamental to modern cosmological models. Dark matter, an invisible form of matter that does not emit or absorb light, was proposed to explain discrepancies between observed galactic rotations and the mass predicted by visible matter alone. Similarly, dark energy was introduced to account for the universe's accelerating expansion. Despite their central roles in current models, both dark matter and dark energy remain elusive, with Earth-based experiments yet to confirm their existence. This has led scientists to explore alternative theories and possibilities. The challenge of understanding dark matter and dark energy is compounded by the vast scales involved in cosmological research. Observations of distant galaxies, the cosmic microwave background radiation, and other anomalies provide indirect evidence of these components, yet their true nature remains uncertain. This ambiguity has prompted researchers to consider a range of possibilities, from modifications to existing theories to entirely new physical principles. According to some hypotheses, dark matter could consist of more exotic particles than previously thought, or dark energy might represent a new fundamental force. Another fascinating area of cosmological research is the study of cosmic inflation. This theory suggests that the universe underwent rapid expansion in its earliest moments, leading to the large-scale structure we observe today. While inflationary theory has successfully explained many aspects of the universe, such as its homogeneity and flatness, it also raises questions about the nature of the inflationary period itself. Observations that challenge established inflationary models could lead to revisions in our understanding of how the universe began. Another ongoing area of interest is the search for extraterrestrial life, which continues to drive space exploration. The discovery of exoplanets, planets orbiting stars beyond our solar system, has opened new possibilities for studying the conditions necessary for life. Advancements in telescope technology, such as the James Webb Space Telescope, allow scientists to analyze the atmospheres of exoplanets for potential biomarkers. The prospect of finding evidence of life beyond Earth has profound implications for how we understand the universe and our place within it. In conclusion, the reassessment of cosmological hypotheses in light of new observations is a testament to the strength of the scientific method. The James Webb Space Telescope and other advanced observational tools have provided remarkable insights into the universe, prompting researchers to revisit and refine long-held theories. This process of continuous inquiry and revision is essential for advancing our understanding of the cosmos and answering fundamental questions at the heart of cosmology and space science. As we continue to explore the universe, we remain engaged in a quest for knowledge, one that not only seeks to answer essential questions but also inspires future generations to push the boundaries of human understanding.